Ladies and gentlemen, we'll now go to our next panel discussion, and that panel will look at how new technologies are shaping the future of secure satellite communication, and how can we really keep our satellite networks safe in an increasingly connected and contested environment. Please welcome our moderator, Kristel-Amelie Aimre from the Ministry of Foreign Affairs, together with Laurence Duquerroy from the European Space Agency, and Chaitanya Kasambe and Ayush Pradhan from Reorbit.
Hello. Hello. Thank you. I think yeah. Right place. Good afternoon, everyone. Welcome to our panel on secure communications via space domain. Myself, I'm coming from Estonian Ministry of Foreign Affairs, and I've seen firsthand how digital technologies shape diplomacy, security, and international cooperation. And increasingly, space is becoming part of that equation. The satellites that connect our world are no longer just technical infrastructure. They are strategic assets, essential for communication, navigation, and even crisis response. And today we'll explore how technologies can help secure these systems. I'm delighted to have here three panelists. Laurence from European Space Agency, Ayush and Chaitanya from Reorbit.
Yes.
And before we dive in, I'd like to give floor to the panelists so they can briefly introduce themselves. So let's start here, yes. Please.
So good afternoon. My name is Laurence Duquerroy. So I'm from the European Space Agency. I work for the Connectivity and Secure Communication Directorate, so Telecom Directorate of ESA, and I'm in charge of activities related to safety and security, so for air traffic management, but also for cybersecurity, for instance.
Hello, everyone. Good afternoon. I am Chaitanya, and I work as an avionics systems engineer at Reorbit Space. But before that, or I would say I started my journey in space industry by working on this radio sounder, radio device for Indian government, and then after that I worked in a Indian space startup. They are designed mostly power systems for nanosatellites, and few of those have been launched. And after that, I also contributed a little bit here and there with some communication systems architecture. And now I joined Reorbit to work as an avionics system engineer, and here I take care of avionics for upcoming missions and their platforms. And today I am here with my colleague Ayush to speak about quantum key distribution, or how that can help us to make the communication more secure for space-based applications. Yeah.
Hey guys, namaste. I'm Ayush. I'm a software developer at Reorbit, and my background is in embedded systems and IoT. I would like to start what brought me into space, and that is the complex hardware that we have, the time-constrained environment, and the deep level of innovation that we're doing for the future. So I met my colleague this year, and we decided to first enter a hackathon, the 9th Cassini hackathon. And the idea was just to participate and build a demo, which was based on IoT satellite, where we demoed a heartbeat from one location using a satellite to another location. And to our surprise, we came first position in local as well as EU level. And this was like the first time Finland actually got gold, or the first place for Cassini hackathon. Besides that, my day-to-day work in Reorbit is mainly on the software side. We are software first, or software-enabled satellite company. So our core focus is on the software system, which is basically what we call Strawberry. We are trying to make the satellite more reconfigurable, so it can be added with any of the payloads that can be like the quantum key distribution, on which me and Chai actually have been writing some papers, and it's a future tech. So yeah, thank you for inviting us here.
Thank you all for your introductions. Now let's start with the questions. Ayush, first question is for you. Can you help set the stage for us and explain a little bit in simple terms what quantum key distribution is and why it is considered such a breakthrough for secure communications? And why are low Earth orbit satellites particularly important for the development of quantum secure communication networks?
All right. So before I start, I just want to know how many of you know quantum tech? If you can raise your hand. And how many of you know QKD, or quantum key distribution? Great. So it's not a complete new thing. So before I start what QKD is, let's understand what the current implementation we have with the classical cryptography. So we have two users. It can be the ground station and a satellite. Now, in order to exchange commands and telemetries, we send them with predefined set of keys. Now, these keys, for now, is unhackable. No one can intercept them. But we have seen from the past that if someone is provided with a great computational power and algorithm, they can be broken. Well, then what is next? Well, next is quantum key distribution, which we call it as QKD. So in QKD, it is a similar format of keys that secure your telecommands and telemetries, but it doesn't follow the mathematical law. It follows the quantum physics, which in its state is actually a photon, which basically is a laser that you send from the ground to the satellite and the satellite to the ground. So if there's anyone who's trying to interfere in this or trying to measure it, we'll get to know it as the quantum states are very delicate and they change their state. So this kind of helps us to find an eavesdropper who's trying to intercept the data or trying to change the command for the satellite. Now, the very first protocol that came up was the BB84, which is started by Bennett and Brassard in 1984, based on the principle of Heisenberg. So the idea is, let's say I have a dice and my friend has a dice, and we spin it and I get number 6 on the dice and he also gets number 6. Since we have the same communication now and we have logged it, I'll be able to send the data. Now let's say there's a third person who disturbs this and he gets a 5 and I get a 6. In this way, I'll be able to see that there's an eavesdropper and he's trying to interfere in the connection that we have. So this was one simple example, and there's many other protocols that we have, like the E91 and the B92. So yeah, why is it said to be a breakthrough or something that's unique in communication perspective is the reason that it's not easily hackable, at least as of now. So yeah, the easiest test bed for now, what we have is the fiber optics, which is able to send the data in the form of quantum tech. But there's a limitation. It can't go more than 150 kilometers, and there's also terrestrial issues. So what's next with that? We can use satellites. One of the satellite could be a LEO satellite, which is cost efficient, and also we can kind of have constellation of LEO satellite, which provides a continuous range of key exchange. So in this way, LEO is a bit reasonable, plus the distance. LEO satellites, they fly at a range of 500 kilometers. So as they are close proximity of the Earth, there's a higher key exchange rate, and you also can use a simplified optical sensor for the same. The next reason is, of course, the current state, the QKD is still in this testing round. There's no particular space-grade material or payload available for the same. So countries like China, India, and some in Europe, like the Eagle one, they are now testing it in the LEO to provide a better results with this. So that's why I see it's the future for us.
Thank you very much for your explanations. Yeah. And Chaitanya, next question is for you. Quantum key distribution is often described as the next frontier of secure communications. From a cybersecurity perspective, what kinds of threats could quantum technologies help mitigate in the space domain?
Yeah, so first, before answering to space domain, let's see what kind of threats we have in cybersecurity. And even before, so to understand this, I divided these threats into two types. First is, what are the current threats, like what threats are going on right now, what can be happening. So one of the first thing that is the passive eavesdropping. If someone is already listening to our conversations somewhere and they are just waiting to get some highly confidential data or something that they can attack on, and they are just listening. So this kind of passive eavesdropping, this is in particularly can be very dangerous because you don't know. You are just thinking you are having normal communication, it's happening, you will be like, all good, but then years later, you might find somebody has already had that access. And I think one example of this was the Marriott attack we saw in 2018. It was observed for 4 years. They were listening to the conversation and understanding all the database for all the time. So this one, passive eavesdropping, and as Ayush explained, when someone is trying to communicate using the quantum key distribution, as if somebody is listening to it, the key changes. And the change, you again exchange with the both the parties, and you understand this particular error rate is a lot more than expected, and then you will know that there is a eavesdropper, and that's where the first threat of passive eavesdropping we can resolve. And in the same way, if there is a man in the middle posing as someone else giving data, same principle, you understand the data has been changed after a certain rate, and you find out that there is a eavesdropper. Next one, now coming to the future attacks. Future attack can be, we are expecting quantum computers to be available soon, and when they are available, two particular things have already been talked or have already been discussed a lot. That's the Shor's algorithm that can generate the prime numbers faster using the quantum computers, and the RSA algorithm that we have for current classical encryptions that can be broken much, much faster. Currently, we expect them to be broken after some years if you do a brute force attack, but using quantum computers, that can happen in a day. I mean, in theory for now, that can happen. And similarly, for the Grover's algorithm, we are expecting that AES key encryption can be broken in the half time of what currently. So for these two particular scenario, if we have quantum key distribution and quantum keys used, in that case, we get the security added even with the use of quantum computers. And now coming to the space side of it. So anything, or I would say sometimes, if people ask me, what engineer are you? I would say electronics engineer, but for space. So I'm trying to say is anything that is on ground can be done on space, but some of the challenges change. It's become a little difficult, but it can be done. But for the cybersecurity hacker, it might be easier, because as a working professional space industry, sometimes it can be difficult for us to make those links, but to get those links in the wrong hands is much, much easier. So I would say all these threats are quite valid in space industry, and this way, using QKD, we can try to eliminate them. I think I would like to add something here, as some of the previous panelists now, like the one before, said we should have this security by design. So I would say that's what quantum key distribution does. It gives you security by design, not by the encryption algorithm or the mathematics involved, but using this physical design or the nature of quantum physics. So yeah.
Thank you. And now it would be interesting to hear a bit of ESA's perspective. Laurence, can you tell us a little bit what are the main security challenges currently facing satellite communication systems, and where do you see the biggest market opportunities emerging in response?
Yeah, thanks a lot. So on this, what we see is that satellite communication systems are now becoming mainstream. So they are more and more accessible, they are less expensive, because of technology evolution, which are indeed very useful. But on the other hand, because of this evolution, we have an increase of an expansion of attack surface. So basically, where attackers can attack, so more points where attackers can threaten the systems. And to give you a few examples of these technology evolutions, which are useful in one sense, but opening new threats or new vulnerabilities. For instance, first of all, there is everything related to software-defined radio satellites. So it's nice, you can reconfigure your satellite. But the risk is that a malicious actor can indeed use this functionality to disrupt your system, to modify it. So there is it's one challenge. Is then more and more indeed to decrease cost, you use on-the-shelf components. And here you need indeed to control indeed your suppliers here. And it's where indeed the security assurance of your supply chain is very important. It's what indeed was mentioned this morning, but indeed you need to check, to be able to check somehow where these software components are coming from, whether they are coming from good, reliable actors. And indeed, it's something which needs to be improved in Europe to be able to verify indeed your the assurance of your supply chain. Another aspect is the integration with 5G networks. So in the past, SATCOM could be seen as a little bit as isolated from the rest, from internet, but now we are talking about integration with 5G networks, where the satellite part is a core part of the full 5G networks. So that opens also new vulnerabilities, new open entry points for attackers. It's related also to direct-to-device, for which we have an initiative for the ministerial at ESA. And finally, of course, everything related to digitalization of the space segment, and on the fact that there are plenty of new actors who want to launch an IoT constellation for communications and so on, who wants to provide the services quick and cheaper, but indeed will not look at all the security aspects. So a lot of indeed challenges are coming already from the sector, but also, of course, from external actors. We see that there are a lot of geopolitical tensions, and really it's where indeed most of the threats are coming on satellite communication systems. We have seen indeed an increase of the number of cyber attacks on satellite on space systems in general. And indeed, it's not only affecting governmental and defense actors and systems, but also commercial and private actors. Why? First of all, because military systems are actors and more relying on commercial systems as a backup, as a complement to what they have. So, and the consequence of that is that commercial actors inherit the threats and the attacker from their customers. So basically, if a commercial actor sells capacity to a defense actor, then let's say the potential attacker will attack them. So you inherit the threats from your customers. And the second point is that some commercial private actors are offering services very useful to the society, like for air traffic management, for wind farming, monitoring, for predictive maintenance on vessels, so using IoT systems in real time. So there are also relevant targets for state actors, which could try to disrupt the society somehow. So indeed, a lot of security challenges which needs to be addressed, and at the right level, because of course we cannot expect that a commercial system has the same security level assurance as the military system. It will be too expensive. So we need to find the right balance between what is needed at security level and how much this would cost on the system. But what I wanted to mention also is that I think this is a commercial opportunity. It's really a business opportunity for the actors who master both security and space, because there will be more and more investment in this domain. There has been some studies which shows that indeed this kind of market, so space, cybersecurity together, or cybersecurity for space, is a market which is really growing. In the past also there is this notion of cybersecurity debt, where indeed space actors have not maybe invest as much as needed in cybersecurity things, in cybersecurity elements and protection, and will have to recover this, investing more now. And finally, with respect to customers, we believe that can have a strong business value to demonstrate that yes, you are implementing some security protection. So it will be like a competitive advantage with respect to competitors if you can demonstrate this.
Thank you, Laurence, for your tip and for the overview. Ayush, back to you. What are the biggest challenges in implementing quantum key distribution for space applications, and how can we overcome these technical, legal, and coordination-related challenges?
Okay. Thank you for the question. QKD is still in the test beds. It's still being researched for, let's say, last 10 years, and there hasn't been a proper space-grade material available yet. So there are a lot of challenges. Let's start one by one. The first would be the physical or the link loss challenge. Well, I mentioned we can use satellites for the same because it's in a free space. So when the connection is in free space, you have a minimal distortion, minimum loss of the single protons. But it also comes with a little constraint that it can't work when the weather is cloudy, or it has a lot of dissipation when it's in daylight times. Second constraint along with this, or challenge, is the availability of ground stations that can actually send laser to the satellite in the form of QKD. There have been some tests done by ESA itself, like the Saga project, where they actually were building a ground station, or they have a ground station which is able to send the laser to the satellite. But this is not available everywhere, so that is one constraint of the ground station itself. Then we have the hardware. The hardware itself needs to be space grade. That is, even if there's a little bit of dissipation or there's a vibration or thermal issue, the signal is lost and the photons are lost, meaning that you don't have a proper security along with it. Then we have a Doppler effect, which actually also comes on the software side. And for this, you really need a picosecond level of clock synchronization. Besides these technical sides, you also have a little constraint on the non-technical side, which can be the legal issues or the standardization. Currently, we have standardization for the space security, which is called the SDLS, but we don't have anything for QKD. And eventually, when QKD comes into the picture, we need a standardization. And parties like ESA, private members, and also academia all have to come together to write those policies so that no one can use a QKD in a wrong format or not wrong form. This will help just to make Europe as a whole secure communication protocol. Provided LEO satellite, GEO can also be a helpful use for specific countries that require it. Then we have some constraint on the software side. The software itself of the QKD should be modular, meaning that it can sit on any satellite bus. It doesn't have to be like on satellite A, but it doesn't work on satellite B. It doesn't matter. It should be that so modular or so reconfigurable that it can just sit on any of the satellite. And that's what actually I'm doing it along with my colleague at Reorbit. We kind of are writing or defining those software which can just plug in any of the payload. It can be the current method of using the cryptography or the future QKD itself. So yeah, all in all, we have constrained challenges like physical, orbital, software, and then the non-legal side. Yeah.
Thank you very much. So let's move to Chaitanya again. And can you tell us more about quantum key distribution? It promises unbreakable communication security. And what does that actually mean in the context of space industry? And how is Reorbit positioned to enable and integrate it into future spacecraft architectures?
Yeah, so first let's start with unbreakability, as you said. I think it would be better to define what's unbreakability, because as some of the previous panelists or the speakers said, there is nothing that can be unbreakable, and that's quite true for this as well. Everything eventually can be breakable and can be broken. As in, with respect to quantum key distribution, even if you know that there is eavesdropper, some of the attacks are still possible. Like someone can jam your quantum channel, they can keep reading you, and you just have to discard all your data. So those sort of problems are still there. But even with that, unbreakability is coming from the terms that we have most secure way to exchange keys somehow. And in future, we can think of direct communication as well. So that will be the unbreakability here. In terms of space industry, as Ayush already mentioned, we are lacking multiple things. We need some of the hardware that's not available, and some of the ground infrastructure needed for this particular purpose is still kind of missing, or there are requirements set by ESA, I think, in one of the compliance sheets and the documents that we have to follow and make those ground stations. So those things are happening, but we still need good amount of ground station. And yeah, so from industry side, what we have to do is make satellites future-proof in terms of quantum computers and the other attacks that I mentioned earlier, to have understanding that the satellites we launch today will be there in space for next 5 to 10 years. And in those 10 years, we can have those quantum computers. And there we might need this QKD already. So building that crypto-agile architecture would be a start. And to scalable the ground station where we can exchange the keys on ground and then somehow communicate with some protocols to the satellites and ensure that the communication is safer would be a way. And now at reorbit, so basically at reorbit, we make software first or software-enabled satellites where software is our backbone and hardware can be changed. To think of it, a better example would be to think of an operating system of your phone. You can keep changing your operating system of your phone. You can keep changing hardware, but the operating system remains the same. There will be updates, but the same operating system can have multiple hardware. So that will include QKD as well. And apart from that, we are doing this research where we are trying to do this mathematical modeling of QKD, which Ayush and I worked on, and getting this research done parallelly and making our satellite future-proof so that if somebody needed a quantum-proof satellite, we have a solution for them. So yeah, that's the answer.
Thank you for that and great industry perspective. Laurence, we would be happy to get more tips from ESA's side. Could you name some key security technologies Europe should prioritize for the next generation of satellite networks in the future?
Yeah. Thank you. So QKD, first of all, is one of them. Indeed, ESA is working with a program on that. With a Skylight program and with a Saga as well. Then we also work on traditional, let's say, cybersecurity. And indeed, we are supporting a lot of different technology development, but I had in mind to speak about two of these technologies. So one is about post-quantum algorithms. So it's basically traditional asymmetric cryptography, which are enhanced to overcome the threat of quantum computing. So maybe you have heard, but there is a joint statement which have been signed and published by 18 national security agencies in Europe, highlighting really the need to start the transition to post-quantum algorithms because of potential advent of quantum computers. And indeed, it's they put quite an ambitious timeline, and they say that indeed we should start the transition by 2030 in the statement, which is basically tomorrow. And of course, it's for critical infrastructure mostly, but space is a critical infrastructure. And it's even more important for space because missions are lasting quite some years. So it's important to start to think about this transition and work on post-quantum algorithms. And it's not indeed something which is straightforward. It's still in the R&D world. Some companies indeed are starting indeed to develop products with something new, and there are really some recommendations to be taken into account where indeed it's important to be agile when you will implement indeed post-quantum algorithms, because these algorithms, there could be new algorithms recommended by NIST in the future. So you need to be able to indeed to upgrade your system and to put new algorithms if needed. And also it's recommended to have a hybrid approach in the meantime, so using traditional and post-quantum algorithms. So it's one of the points, I think, on which we should work in Europe. And the second one was about key management as well, because for most of the systems today, it's based on the secret key infrastructure, where really the operators have a strong they have to manage the keys, to have procedure to handle, manage them, change them as needed. And it's what we see is that it's not really scalable when we are talking about system of system, multi-domain system, where indeed you have several operators working together and you want to establish secure, authenticated links between different nodes, like different satellites, which maybe are between satellite and ground segments, which are maybe belonging not to the same operators or to the same actors. So here, there is the need likely to transition to public key infrastructure, which is based basically, you know, it on certificates. It's widely used in the internet, where you have a certificate, you are a certificate authority, which will provide you with the right information in order to authenticate the person which is in front of you. So it's a little bit for the same here for space, where we could have many constellations with many satellites, multi-layers, several layers of indeed of satellite with different operators. And it's not that simple to implement PKI on satellite systems, because, okay, you maybe not have the same computational capacity than on the ground in internet, for instance. You don't have always this server-client link. There is the story of latency, and so on and so forth. So there is a need indeed to tailor indeed this PKI, and also to think about who would be this authority to deliver certificates. Who could it be? Should it be someone, a public regulatory organization in charge of this? So there are a lot of questions behind, and on which we on either side with industry have started to work on.
Thank you very much for that. I think for now it would be great to exchange a little bit with you. So perhaps you have some questions. And you can also say to whom you address your questions. So we have a question here. What is traditional security in terms of satellites specifically? Who would like to reply?
Or maybe I use the term traditional. What I mean is the difference between, let's say, quantum and not quantum. Let's say there are two worlds here sometimes which are a bit fighting between each other. There is the traditional cybersecurity actor working on,
let's say, classical communication. Classical physics and quantum physics.
Let's say working on the cryptographic algorithms that you can that you maybe know. And there is indeed this new evolving domain with allowed by the application of quantum physics. So quantum key distribution is a new way to distribute keys.
I think one example or the direct comes to my mind is AES key encryption that we already use a lot in space, a lot of space protocols, including CCSDS and some of the other protocols we have. So typically it's the AES key encryption, and you can add RSA and other ECS type of coding over it. So first, it will be simply, let's say, to make it more general, will be to have this correct frequency band, and then to go modulation and to the encryption and decryption, and that's how entire set of things are communicated. And there in the encryption we have RSA or AES key encryptions. Yeah. Maybe Ayush, do you want to add to that one, or you want to take the next one?
Take the next.
Yes, so we have another question. What can be done about malicious updates to satellite onboard software?
Okay, I can go with this. So currently, as I mentioned, we have a fixed set of keys. So it is secure in a way. But if there's someone in-house who does it, what can we do? Well, I would suggest the first thing is to go through each subsystems and see what is the issue that's happening. Of course, then could be to implement more hybrid cryptography, which is basically using classical cryptography. On top of that, we can use a post-quantum cryptography and then the QKD as well. So all three will actually give us a bigger umbrella of protection and kind of protect us from any other malicious attack. The one that's done can, of course, be reverted back to the older version, and we have a safer software itself. But yeah, that would be one.
Maybe I would like to add something here. So basically, I'm a big fan of this philosophy called Pokayoke. It's a Japanese word, which means you make something unbreakable by design. Like, for example, the USB B type, you cannot plug it in the other side, because if you put it outside, there might be short circuit or something. So in this way, I want our software also to be designed that some of the basic functionality you cannot change using software updates. You just change the top level things, and you will know when your satellite gives you next data, hey, that somebody has broken it, but it's not 100% broken. The basic things are still unbreakable, and then the broken things you can repair on the go. I would like to add that. Yeah.
Next question, what are the limitations of quantum security-based communication today?
Say I would want to answer this in maybe simple words, it will be more testing. We need a lot more testing and to understand how this payload works and how to do analysis on these links so that we can make it better and better for ISL and others type of links communications.
Maybe to complement, one also of the thing which is assessed by ESA is indeed you receive your quantum key, but how can you be sure that it's properly injected and secure way in the system afterwards to be used? So it's a new interface that is created, on which we need to be sure that it is secured enough. Yeah.
What are the benefits of quantum key distribution when compared to conventional post-quantum key distribution methods that should be also resistant to MITIM and similar attacks?
I think MITIM here means man in the middle attack, and so primary protection is coming from authentication of the channel and authenticating the key with respect to that particular channel. So that's the primary thing, and to make it more secure, the idea would be to combine the conventional keys and the quantum key to make a hybrid key, and that will be a better communication.
I would also complement to this is that to get exact benefits of QKD, we actually need to have not just one satellite that does it, but a constellation of satellites that's protecting it. QKD in general could be a regional-based security that we are providing, but on top of that, it can be a protection with a geosatellite that provides a bit more of the range of it covers, the protection it gives.
And maybe to complement, so at HISA we work on the two streams, so this classical and this QKD, because we think it's important to, since the quantum threat is not yet materializing, there are some uncertainties, so it's important to keep these two lines active and to develop them.
Thank you. Are there more questions here amongst the audience? If not, perhaps... Oh, there is one. Yes, of course.
I would go down deep in the low level, and on the FPGA side would be the protection that we need. The current quantum key distribution only protects the data from the outer level, but we don't have a protection for the actual data that's coming, and that is something we have to, of course, do a more research and tests on.
More questions? If not, perhaps everybody can have the last word to conclude or to give a message for the audience. So let's start from here, from Laurence.
Maybe to conclude, what I would say is that cyber threats are not the only threats. We see new threats coming, directly threatening the satellite in space. So it can be other satellites going around and trying to eavesdrop your transmission, or also what we call kinetic threats or electromagnetic attacks directly on the satellite. So, and again, this is not only for defense scenarios, military scenarios. This could happen to commercial scenarios. So we need indeed the countermeasures which are cost efficient to address these new challenges, and which needs to indeed to be defined and identified.
And I think from my side, I would say, I see that industry has evolved much faster in last 10 to 12 years. We were talking about 10 years back, we were talking about LEO constellation, and now we already have them. Now we are working on laser. So I think in next 5 to 10 years, we can see this quantum key distribution or quantum channel already as a part of standard offerings by satellite. Maybe not 5, but at least 10 or 12 years would be a good timeline. So as an industry, let's try to focus more on this and test it more.
For me, I would actually add on to what you said. For now, quantum key is still said to be the future, but we have to get ready now, do numerous tests from the Leo perspective as well, to make the hardware itself and the whole link or data. As they say currently that data is the new oil, so we need to secure them in a manner so that the entire Europe actually is not able to face such issues on any key distribution. Provided to this, we of course still need to do the test more in terms of getting along with the agencies, getting along with private players that can provide us secure hardware, and getting along with players that can provide the software bus on which it can sit to make it a whole protective layer. So yeah.
Thank you for all panelists and for all of you for being here. If I'm not mistaken, we have a coffee break soon, and our panelists will be here as well, so don't hesitate to go and talk to them and ask more questions. Thank you very much.
Thank you guys. Thank you guys.